Thanks a lot, David, for the nice introduction. So we will talk today about, oh, bear one second. I need to find out how this works. Okay, here we are. Yeah, so thanks a lot for tuning in to this masterclass. I will give an introduction to focused ion beam microscopy, which is a relatively young method compared to other techniques like electron microscopy or X-ray diffraction, which were basically developed right after the inception of quantum physics, but really commercial viable ion beam microscopes started to show up in the 70s and 80s. I would like to first give a basic overview about the core processes and what kind of applications are then developing based on that. The technique has undergone a very strong development. I would like to show that a little bit with a sort of a historic overview and introduce different components that were key to that technique. The technique has a vast area of application, so I try to pick a few to give you a sense of what you can do with this instrument. And I will particularly focus in this talk about biological applications because they are now the new frontier for that method. As every technique, focused ion beam has its challenges, and so you need to be aware of those and in order to properly evaluate whether and how they affect your results. And we do have, for most of them, mitigation strategies, and I will talk about that. And I hope in the end that you have a sense of the scope of the technique, and so that you can decide whether it might be of use to you. If you're starting at the core of the technique, we are having an ion that is accelerated towards a material. It gives up its energy via scattering events and eventually implants into the sample. And if the scattering directions are in a particular direction, they can actually lead to release of host atoms from the surface, which we call sputtering. This leads to, and on top of that, we can do that now on a very small scale because modern instruments are able to focus the ion beam down to the nanoscale. And so we are able to now use these processes to do nanoscale sculpting. The first process, implantation, has been used for decades to change the local properties of materials. Its use in terms of local change of the properties is not as prominent as the other applications, but there are signs that this might actually change in the future. The other two processes lead to what I roughly divided into three major applications, which I call nanomachining, sample preparation, and analysis. What I mean is that nanomachining, in a general sense, allows you to extract the material, shape it, or confine it. And this allows researchers to modify a sample and go outside of CNS and do experiments that are otherwise not possible without the introduction of the focused ion beam. Of course, the focused ion beam plays a central role within CNS because it is now a very important tool to prepare samples for many other tools like the transmission electron microscope and the atom probe, and I will show examples for that. Over time, it has also evolved to it's an analysis tool in its own right, and for example, by allowing cross-section analysis on a routine basis, or if we want to do it a little bit more sophisticated in form of a 3D analysis. I would like to give you first a little introduction how the technique came about, where we are right now, and maybe where we are going. The whole development was driven by the need of the semiconductor industry to target defects deep in their buried structures in the chip architecture, to analyze defects and to change things. The first microscope was based on just a single ion microscope, and the first big tool development were actually gas injection systems that allowed to, for example, selectively remove silicon so that you can open up the bare metallic structure and analyze potential defects. On top of that, gas injection systems were developed to deposit conductive materials, to rewire the connections, or insulating materials. And so this whole process we can really summarize in the field of circuit editing. I would like to point out that there are two books, there are multiple books. Two of them are from Lucille Giannuzzi and Nan Yao. As you can see from the date, they are a little bit outdated. Nevertheless, they have a lot of information if you're interested in learning more details about the technique. It has been relatively early clear, and I have been working on a single ion beam microscope, that the problem with that is you can cut, but you're limited in actually seeing your sample and targeting the proper regions. So this was the driving force to actually combine the ion beam with the electron microscope and generate a dual beam microscope. This allowed us to now have suddenly all the tools available that you are familiar from the SEM microscope, and we have hugely augmented the tool set of this microscope. This was basically the inception of the use of the tool in material science, in particular, as then with the invention of manipulators. With the manipulator, you can extract a sample from your region, and you can very much hone into a specific region and pick out this material and do TM analysis and all other aspects. And not long after, it of course became clear that this is also very useful in the case of applied sciences. In the early 2000s, you started to see commercialization of other type of ion beams besides the gallium, which has been for a long time the standard ion. Ion beam research has been done for decades, but this is now the time where you start to see commercial platforms, for example, in form of a helium ion microscope or a plasma ion microscope. These instruments, because of the slightly different behavior and the slightly different design of the source, not only change the way these beams are interacting with the material, they also extended the accessible volume range of that we can now analyze. So helium ion beam microscope allows you focus a little bit sharper. The plasma ion microscope allows you to look at larger volumes. Another important development was the transition, the move of manipulators that were first developed ex situ into the microscope. And this in situ manipulators were, for example, very important and a very important boost for the atom probe tomography technique. Traditional techniques were very much limited to metallic samples. But with the focused ion beam, you certainly were able to prepare material and extract material from any type of material that you can think of. If you are interested in that technique, I highly recommend to tune in on next week, where Austin, our expert in atom probe, will give an introduction to that technique. Over the years, software control has become more and more advanced. The instruments have become more stable, and as a result, we can do now more and more sophisticated tasks inside of the microscope, and one of those is 3D imaging, where we in consecutive repetition mill image, and then we can get a series of hundreds or thousands of slices and get a true three-dimensional image of the structure. And I will show that in a minute. Developments are going on. As I said in the beginning, right now we are at the cusp of making this tool available for biological applications, and this is very exciting. And I will show you, hopefully, I'll show you later then also some hopefully nice examples. So at CNS, we are in the fortunate situation to have two extremely powerful dual beam instruments. On the left side here, you can see the Helios Nanolab 660 from FEI. There are different geometries on the market, but most general purpose instruments are based on an SEM platform with the ion beam attached on the side. The instrument is packed with auxiliary components that make it an extremely versatile tool. So for example, you have a very precise stage that allows you to move the sample in 5 degrees of freedom, that keeps the sample very precisely for a long time at the cross point between the ion beam and the electron beam. You see the gas injection systems that have been introduced just a minute ago, as well as the micromanipulator. You have now a plasma cleaner with which you can keep the instrument clean. And here on the left side, you see an electron backscatter detector, one of the many tools that we have available in the SEM. What you do not see is all the components that are inside of the microscope. This instrument has a very nice high resolution SEM, which really allows you to look at very, very small features. And with all its capabilities of extract and visualize certain features like EDX, Jules gave a very, very nice talk in the beginning about the quantification of it, EBSD for crystallography, and then we have all kinds of detectors to visualize the morphology. So if you are new to this thematic, then I highly recommend to tune in to Tim Carbonar's masterclass, who is giving an introduction to the SEM, where you can have a peek inside of the microscope and see all these detectors in action. So we are very, very fortunate that we were able to replace our old Zeiss Envision system with a brand new Crossbeam 550. We had a little hiccup in the installation. It's still ongoing, but we hope that when we're back in the lab that we can ramp up that instrument very quickly. It can do many tasks as the Helios, so that means we have now dramatically increased our bandwidth and hopefully improve the throughput of the data analysis for our users. But more importantly, there are small but significant differences in the design of the instrument that allows us to expand our range of applications. For example, the pole piece in this instrument is an electrostatic lens that, as compared to an electromagnetic lens in the Helios microscope. So this, for example, allows us to look at magnetic materials. It has also ramifications for how we're doing zero sectioning, so we can get much faster zero sections. And it has also excellent low energy performance, which is very good for imaging of soft materials. On top of that, we were able to use our old cryo stage. Also, we can transport it from the Envision to the Crossbeam, which allows us to now analyze vitrified samples. And connected with that is a vacuum transfer system. And the vacuum transfer system can also be used for air-sensitive materials. With the installation of the Lee microscope, Austin was able to develop a whole glove box system to transport air-sensitive material between the different instruments. And so we have that additional capabilities, which again opens up more opportunities in energy research, etc. So let me go now to the first applications where we use the tool sort of as a means to enable other experiments. And in that, first I would like to thank all the users and all my grad students and postdocs who graciously provided me with the data so that I can show them to you. I want to start with work by Charles Hurst. He is a graduate student in the short group in the Nuclear Science and Engineering Department at MIT. And he is interested in using nano-calorimetry to measure irradiation damage. There are several factors that motivate the use of focused ion beam. First of all, the irradiation happens only in a certain surface area. And if you're using bulk tools, instruments, you has less sensitivity because you're measuring also the behavior of the bulk sample. So with the focused ion beam, he can go in, target specifically the irradiated area. Those samples are typically radioactive, so reducing the sample size makes the handling safer. And another aspect that is also used in other contexts is that if you make the small volume smaller, you can increase potentially the heat transfer rate and get a faster response. So he provided me very nicely with a wonderful little time lapse that shows the process, which can be seen as a prototype for many other applications. So temp sample preparation and atom probe preparation are basically using the same routine where you extract your sample, you pull it out with the OmniProbe needle. Yeah, so we're right now here in the cutting stage. So if we are following the movie, you will see that the OmniProbe needle attached to the top, it's pulling out this rectangle. We move the stage over to a MEMS device. He's dropping the piece and gluing it on with the gas injection system. And you will see in Austin's talk that a very similar process happens when we prepare atom probe samples. So this is just to show you what you can do with these various tools inside of the microscope. The second sample is more centered in the field of applied physics. Frank Zhao, he's in the King group at Harvard and is interested in electronic properties of 2D materials. In those samples, these samples are very sensitive, and sometimes you are not able to use the standard clean room techniques that are solvent-based. And so he is using a printing technique where he cuts a complicated pattern into a silicon nitride membrane via focused ion beam and uses that membrane in a microscope setup to very precisely position the contact area and then makes a contact. Yeah, so you see that we have the tools to make more complicated patterns if that is necessary in your structure. The last example I'd like to show you, because it is a very simple but clever way of using the focused ion beam. Dylan Renaud in the Longa group is interested how external forces like strain influence the optical response of 2D materials. And for that purpose, he's using a fiber, optical fiber, that to both actuate the mechanical strain and use it for the data collection, the optical data collection. The method is based on two steps. First, he uses an HF solution to very precisely fabricate a precise taper angle. And then in a second step, he uses the focused ion beam to prepare a flat contact area with exact radius for that produces the optimum collection efficiency. So these three samples are just a short sample of a small sample of what you can do with the focused ion beam, but I hope I can give you a little bit an idea of how it may be useful in your case. So if you're thinking about using focused ion beam, I have here collected a few items that might be useful in your decision process. So first of all, the question is, what is the scope of your experiment? What resolution do you need for your sculpting process? Commercial or modern focused ion beams allow you at small currents to focus the beam down to 10 nanometers. So the smallest features that you can produce are on the order of 20 nanometers. How large are the total dimensions that you are interested in? You need to be aware that the removal rate is determined by the sputter rate, which is again limited by the beam current. So there is a certain limit on the size of the volume that can be accessed in a quote reasonable time frame. Of course, if you spend more time, you can get bigger volumes, but a typical dimension is, say, for example, 100 by 100 by 30 micrometer as a rough guideline. Then the question, do you need repeat units? Do you need a periodic structure? In that case, you need to be aware that we are milling with a scanning beam. So this is a serial process. So that will additionally take more time. So in that context, it is sometimes, like to think of focused ion beam more as a prototyping instrument that can target certain areas, but you can then maybe play around and then learn from the lessons learned and go then into the clean room. One aspect that everybody has to think about is the defect formation in the area that has been cut. As you saw, the gallium ion is entering the sample into a certain depth, several tens of nanometers. And so you have to ask yourself, do these implantation defects affect your signal? Yeah. So, for example, this is often a problem with optical measurements where the defects generate so much signal that it's overwhelmed the actual signal that you are interested in. In that context, you might think, how large is the volume that where you get the information from, right? And how does that relate to the actual defect zone? And is the defect zone significant or is it less significant? Yeah. So this is just a couple of ideas that maybe help you to judge if that technique is useful for your case. Let me now go to more to CNS specific applications, and that is the sample preparation for other imaging techniques. FIB has become a pivotal tool in imaging facilities. Almost every imaging facilities across the country has a focused ion beam. As we saw in the case of atom probe tomography, it was the necessary condition to actually make atom probe a viable general purpose tool. In other applications, it helps to speed up the process. But most importantly, it allows to target specific regions of the material with a precision that was not available before. So as a result, the information that you can get is in a sense more meaningful because you know the larger context of the sample. So let me demonstrate with one little example. And oh yeah, so just as a side note, since focused ion beam is used to prepare materials for different techniques, and some of these techniques are accessing similar volumes, we can build up a correlative workflow so that we are not only using each individual technique, but we can actually use the complementary information that two techniques potentially could provide. And so, and therefore, further expand our horizon. So let me go over to an example that was a very fun project, or is a very fun project with colleagues in the art department. So Catherine Ehremann and Lucy Cooper, who was a postdoc in the museum, were interested to learn more about some of their ceramics, in particular the ceramic that you see here, which was the so-called numbered Yunware from the Song Dynasty, which has these beautiful red and blue colors. And so we are basically trying to do some kind of detective work, to do some reverse engineering to understand what are the materials, where do they potentially come from, what are the underlying manufacturing processes and conditions, and also how do these colors actually come about. So Catherine gave us a little piece of precious piece of the sample, and we started looking into it. And it turns out that the glaze is not only beautiful on the outside, but it has also a very intriguing structure on the nanoscale. So here you see part of a TM image that was recorded by Jules with a high angle annular dark field stem. You see here two faces, silicate glass faces, a globular minor phase in a darker matrix, and then sprinkled in between are brighter dots, which turn out to be copper-rich regions. If we now go to the blue region, you see again two immiscible silicate faces, but this time the morphology is much more complicated and you're forming an intricate network. So Jules has used all her tricks to analyze the chemistry and the crystallography of the system, and we can really learn something about the optical properties of this material. For example, turns out that these copper-rich particles are in fact metallic copper nanoparticles, and that we can infer that most probably the color that we are seeing is due to surface plasmonic excitations. If we're going now to the blue phase, then we are dealing probably with Rayleigh scattering, where the nanoscale sub-wavelength features are scattering the light in such a way that we get a blue color. We can further interrogate, oh yeah, by the way, sorry, I forgot. We are able, and one of the nice, really interesting aspects of focused ion beam is that we really don't need much material to get information. So if we really push the limits, we can get information, really valuable information down to the atomic level from an area that is only 50 by 50 microns, roughly. Yeah? So this can be very important if you have very precious material, or if you have a process that really generates only little material. And with focused ion beam, you can very easily access this material. So now we can further interrogate the sample with help of 3D serial sectioning. So here on the left side, you see a sequence of images that we have taken in the red phase, and you can see how we are going step by step through these high contrast globules, and every now and then you see the bright copper particles blink up. When we go down to the blue phase, you see this intricate network of the high contrast phase, and the images that you see here are based on backscatter imaging. So now that we have the full three-dimensional information of the material, we can do actually quantitative analysis. So for example, we can quantify the particle diameter of the nanoparticles, which gives us further information in terms of the plasmon scattering. On the right side, on the blue phase, we can learn that we are having a completely connected network of the second phase. We can extract volume ratios of the two phases, which gives us an idea where we are in the phase diagram. And we can get all these geometric properties like tortuosity, etc., that some of you might familiar from CT tomography. So in summary, focused ion beam gives us the opportunity to get crystallographic, chemical, and morphological information over multiple length scales in a very targeted fashion. Another important aspect of the technique is that if you think about how long it takes to get to the data, that is actually relatively reasonable time frame. So I have here very roughly written down how long it takes to prepare a sample. Right, so an atom probe sample, there are, of course, it's a little bit lengthy process, but nevertheless, you get a sample, several samples within 4 to 5 hours. TEM sample preparation can be sometimes very quick if you just want to get a quick answer. If you want to get really high quality samples that for atomic resolution imaging, you might need a little bit more time. Maybe you should take more 4 or 5 hours. These 3D imaging analysis that you saw, it scales with the volume, right? So if you just want to probe a small volume, it's relatively quickly. I haven't talked about 3D imaging, so basically it comes a little bit with an overhead because you need to prepare fiducial markers that then the electron beam and the ion beam can use within the control software to precisely position the cut position and also the imaging position. So you need to prepare the material, which takes, depending on the volume of your material, between 3 and 5 hours. A run then in the end can run automatically over several days. A fundamental shortcoming of the technique is the damage that you're generating during the implantation of the gallium. And this is something that everybody has to consider and evaluate if it affects and how strongly affects your result. So ultimately, the gallium ion transfers its kinetic energy to the host in a series of scattering events. At some point, it has exhausted all its energy and it stops and gets implanted into the sample. So some of you know implantation experiments, but in those experiments, we are dealing with really just very controlled implantations. This is not the case in the process of a cutting. We are dramatically changing the chemistry, as you will see in a minute. So we're changing the chemistry so much so that we are, if we're thinking about a phase diagram where we have now the component plus gallium, that we're actually moving into a completely new region in the phase diagram with implications that we can potentially produce, if the kinetic conditions are conducive, that we can actually generate secondary phases. So then on its path, it knocks out host atoms, leaving vacancies. And these host atoms eventually will stop and typically can often fall into interstitials. So we are damaging the sample, we are reducing the order, we potentially increase the diffusivity, we definitely generate stress. Everybody who is preparing TEM samples has painful experiences where as soon as the sample gets thin, the surface stresses that we're inducing start to bend the sample, and then it gets very difficult to handle samples. In terms of optical properties, we always need to be aware that these defects change the electronic state and therefore can generate additional signals. So to make this abstract concept a little bit clearer, I tried to make a simple model experiment. So I prepared a crater with the gallium beam at various voltages, and then filled the crater with the e-beam platinum that is available inside of the microscope. So by covering it with that e-beam deposited platinum, we can preserve the surface structure completely, and we can prepare a TEM sample. And what you see here is sort of the HIDF signal in the TM. So if we are focusing onto the corner of that crater, you can see the extent of the damage at the surface. So you see at the bottom left corner, the gray, dark gray continuous area is the silicon. In the top right corner, you see the spotted contrast from the platinum particles. And a band in between, that is the damage zone. So you can see that there's a damaged surface area and that the thickness depends on the beam incidence. And that we can understand by if we are looking at implantation simulations based on Monte Carlo simulations. So under vertical incidence, and the reason is because at higher voltages there is a certain directionality in how the ion beam that is implanting and moving into the sample, which ultimately causes a deeper penetration under vertical incidence versus a less deep penetration into, if we have a situation like we would have when we prepare TEM samples, where the beam is barely glancing the TEM sample surface. So let's look now a little bit closer at that damage zone. And you see here in the next slide the example of what happens when we are implanting or milling with a 5 kilovolt gallium beam. So we are now at as much smaller dimensions. The surface of the sample is where you see the y-axis on the left side. On the right side, you see a periodic array, and this periodic array is actually the atomic structure of the silicon. So that tells us that the entire defect zone in silicon has been homomorphized. Yeah? So the defects accumulation was so high that we have completely homomorphized the sample. Furthermore, you see now a white band closer to the edge, and with EDX we can confirm that this is indeed gallium implantation. And it turns out that when we are plotting and measuring the profile of the gallium distribution, that this profile corresponds pretty well to what we are expecting from Monte Carlo simulations. With one little detail that you see a dash curve and a solid curve. So the dash curve is what you expect from Monte Carlo simulations, and the blue curve is slightly shifted towards the surface. And this is probably now reflecting the situation that we are dealing here right now with a dynamic process where we have a constant equilibrium between implantation and sputtering. So, and that seemed to push the distribution a little bit closer to the surface. If we now go to even lower voltages, then you can start to see that the original 15 nanometer wide damage zone is shrinking more and more. And only at 1 kilovolt, I want to point out that there is no direct evidence for homomorphization. Yeah. I also want to point out that if you're looking at the intensities, which are actually gallium concentrations, these data are reinforcing what I have said before, that in this damage zone, we have extremely increased the gallium concentration and with all its ramifications. So on the big picture, the lesson learned is that we can mitigate the gallium-induced damage by going to low voltage milling. And that is what we do. So when you come to us and learn how to prepare TEM samples, this will be an important part of your training. A novice user might not see immediately the effects of the gallium damage. For example, if you think about silicon, the main effect of silicon is amorphization, but amorphized area don't produce major contrast in a TM image. So you can, in principle, overlook the problem. This is not the case in the example that I show you in here, which is sort of an extreme case, sort of as a warning sign for everybody who is doing transmission electron microscopy. So this is a two-phase material, which is made out of zirconium oxide and yttrium tantalate, which was done, which worked in collaboration with David Clark at Harvard. You see, for example, the yttrium tantalate phase has these white stripes. So this is a real internal structure. These are twins that occurred during the mechanical deformation. And then if you look at the zirconium oxide, you see a very rough mottled structure. And much of that structure is in fact due to clustering of defects in the surface area of the zirconium oxide. The picture changes completely if we are now carefully cleaning the sample. And when we're saying cleaning, we really need to go, if you want to do this efficiently, we really need to work with voltages that are way below 1 kilovolt. So we want to be underneath a kilovolt. And we're doing this here actually with a dedicated instrument that allows to focus argon beams at low voltages onto the FIB sample. If we're looking here, we can suddenly recognize that there are actually features were hidden behind all that corrugated intensities, which has completely obscured the actual structure. And so you can see here, for example, so this is a bright field image, so the intensities are inverted, so the zirconium is now bright. You see now these tiny little dark features, which are tiny yttrium tantalate precipitates that are distributed all over the zirconium oxide grain. So if we take what we have just learned and apply it to a more basic analysis, so a cross-section analysis that we do on a daily basis, where we simply cut into the sample to see, for example, multiple layers underneath the surface when you prepare some structures. In this context, we need to be aware that the electron beam signal is stemming exactly from the damage zone that we have cut. So if we happen to have a very sensitive material in that zone, we can potentially damage the material so much that we actually lose information. So that is now very important. If you have material that is ion beam sensitive, and which has feature sizes that are on the order of the damage zone, you must clean also your cross-section with a low voltage beam. An example where this was necessary is work that I have done with Mahesh Gangishetty in the Congreve lab in the Roland Institute. He's working on organic, inorganic hybrid perovskite LEDs. And here we knew from X-ray diffraction data that the perovskite structure was made up of particles of the order of 20 nanometers. When we did our first initial cut, all we saw was a continuous band across the thickness of the sample without any features in it. Only when we then cleaned up the surface with a 5 kilovolt beam, we were able to actually bring out these 20 nanometer fine-grained structure within this organic-inorganic hybrid. So I just wanted to give you a sort of a sense of sensibility of problems that can happen and how we can actually solve these problems. So now I would like to switch gear and go to biological materials. Biological samples show extremely high hierarchical structure, where we go from the organism to cells which have organelles, then proteins as the main actuators in the cell, down to all the way to membranes. And the dominant imaging technique is light microscopy, and one of the advantages is that we can analyze the material in vivo. Right? So this movie shows, for example, a malaria parasite that has infected blood cells, and it is right now in the process to asexually, in an asexual process, to form daughter cells, which then at some point egress and would be then ready to further infect more blood cells. The other important technique for for biological samples is fluorescence microscopy. Yeah? And the power of fluorescence microscopy is that we can tag particular proteins, and with those proteins, one can visualize particular regions in the cell. And as in this case, Rachel has prepared tagged different objects that belong to different organelles in the malaria parasite. The problem with fluorescence microscopy is that, as powerful as it is, it has trouble describing the full context of the ultrastructure. There are only so many objects you can tag, and in particular, it's very difficult to actually to show the details of the membrane formation, and so that is where electron microscopy comes in. When we do electron microscopy, we first have to overcome the first problem, that we are operating in a vacuum, and there are two major approaches to solve this problem. The process that has been worked on or used for many decades is dehydration and staining. And for anybody who has not had a chance to see Nikki Watson's talk, and you're interested in this topic, I highly recommend. It is a wonderful introduction into how to prepare actually such samples. In recent years, vitrification has become more and more prominent, of course, with the Nobel Prize. And this is sort of the future for focused ion beam microscopy. Once you have the sample, you have an array. Also in electron microscopy, you have an array of tools available to analyze your sample. Nikki introduced array tomography. It's a technique that is based on using thin slices that have been prepared with ultramicrotomy, and you basically cut hundreds of slices and then stack the images on top of each other to get a three-dimensional view of the sample. And then on the other hand, you can do TM tomography, where you tilt one film and get, by doing so, the internal structure. Yeah. Imaging techniques have always the problem that you're band limited. So there is a lower limit, a spatial resolution, and there's an upper limit, how large an object you can analyze. So as in all other cases, you need to get a sense of in which frame you fit, and you need to use then the corresponding information. So serial sectioning is now becoming more and more prominent in the area of cryo imaging, both as a sample preparation tool, but also as its own analysis tool. And I will get to that at the end of the talk. But let's get back to the parasite. And so this is work that, where I had the chance to work with Rachel Rudiaft, in PhD student in the Dvorin lab in the Children's Hospital. She has analyzed, she's working on these asexual segmentation process where the parasite is infiltrating the blood cell. And it's a rather unusual organism. It is not segmenting in the classical way that the molecules are, that the cell is dividing into two, but it is actually simultaneously forming at once over 30 daughter cells. And it is doing that by moving in the membrane towards the center and encapsulating the inner organelles. At some point, it will have finished that process. It's pinching off in the center, and then you have up to 30 daughter cells that then break out of the blood cell and are ready to infect more blood cells. The TM images can give you a qualitative idea about that process. You can recognize certain organelles, for example, these bottle-like features, but then also you can see the different daughter cells, and inside of the daughter cells you see this kind of ring-shaped objects. But only if you're really doing the full three-dimensional images, you appreciate the nuances of the entire object. And so I show you here two movies that Rachel has prepared, one of the early stage in the development and then one in the late stage. The color text corresponds to organelles that are characteristic for that organism. And when in the early stage, you can see that the membrane starts to form buds and starts to develop irregularities. You have already a few organelles ready. You see a brown food vacuole. And where it gets really interesting is now that you can see here, and let me stop this for a moment. You remember in the TM images, you saw these cylindrical objects. So it turns out that these cylindrical objects are actually a long network of these organelles that extend throughout the entire object. And without this type of three-dimensional imaging, we would not be able to see recognize this kind of feature. So if we are now going to the late stage, you can see that we have suddenly a well-developed daughter cells. Each daughter cell has now its two rope trees organelles. The apicoblast and the mitochondria have divided, and you can now see how each daughter cell has all the necessary organelles and is ready to pinch off and then move its way. So as nice as it is to have now a three-dimensional view, the key interest is still to to understand what the proteins are doing. Right, that is the power of fluorescence microscopy, and there is an approach similar to fluorescence taggings, as Nikki explained in her talk, by using immuno-labeling with gold particles. This is a very complicated, lengthy process, and which I will show later with another example. But here, one can use a slightly different, simpler approach. Simpler, at least from the imaging point of view. It's probably not simple on a biochemistry point of view. Is Rachel and Jeff have discovered a protein that appears to be essential in this membrane development, and they have made so-called knockdown mutants where the protein has been taken out to the most part. So these have strongly reduced number of that proteins. And as you can see in the optical micrograph, that no segmentation happened, right? And as a result, so now the question is, what happens actually in what effect did the missing protein have? And so that is where we again had to do focused on ion beam microscopy. And this video shows now first the sequence of the SEM images. You see how the blood cell evolves, and then we are slowly moving in from the blood cell into the parasite, and then peer into the parasite. You see here the starting raw material data, the images, and Rachel has then segmented the information into the relevant objects. Here you see the blood cell, and then the parasite. And you can recognize that we don't have anymore these very nice symmetric array of daughter cells, but it's now much more messy. You have only 4 and 1 big one. If you look inside of the daughter cell, you still see all the other organelles. So that means that all the other processes don't seem to be affected. And it's really particular only for the formation of the membranes. And so in that way, she could indirectly show that we are dealing here, that the protein is essential for the formation of the membrane for all the daughter cells. So the next example, the last example here in this case, is actually using immuno-labeling to actually determine the location of a protein within a cell context. The work was done by Artur Inchikulian. He was a postdoc in the Corey lab in the Department of Neurobiology, and he is now a professor in the Department of Otolaryngology. To give you an impression on what kind of how small the dimensions we're working, I want to guide you through a little bit, as good as I can, where we can find these objects. So we are in the cochlea at the end of the ear, where you have inner and outer hair cells, and sticking out of the inner hair cells, you have these beautiful cilia, which are used for the to measure the acoustic wave and translate those into electric signals. Now you are going even deeper into it, and you see now very fine hair that connects the different cilia. And so we are have reached now the nanoscale, and you see here 2 bright dots, which are these gold conjugated antibodies that have marked the position of the protein. So he was able now to do this and prepare a 3-dimensional, do this in 3D. And this last serial section run that you see here is built in 3 segments. First, you see again all the secondary the backscatter images going through the hair cell. Then the video turns around, and you start to see how the relevant cilia are marked. And then in the third run, you will see how the three-dimensional object is evolving. Yeah? So you see here, and if you, it's probably over the internet, it might not come out properly, but you see every now and then you see bright dots show up in between the cilia, and these are the gold particles that are attached to the protein. So he could do this now on multiple samples, and as a result, he could get statistically meaningful data and understand where the major location of the protein is, which then translate into information how it is contributing to the hearing process. So this, to summarize, this process is takes a little longer. So we need to, if we want to succeed, we need to carefully prepare. So Nikki and I and many of us are happy to help on the way. So these here are just a few things you might want to think about. For example, what are the smallest dimensions that you need to resolve to understand your problem? That then defines what technique you want to use. If you attempt to do 3D imaging, you are probably interested in the long-range dimensions. And so you need to understand how far the dimensions are going. So just to give you a sense, in our case, serial section data cubes that are recorded, let's say within 1 day, have the size of roughly 30 micron cubed. Then sample preparation is a critical issue, right? It's a general case for imaging. The images are only as good as the data sample are prepared. And when you are in biological samples, it helps to think already ahead towards the peer review process and see what kind of how much the sample preparation will modify your structure, and how relevant the data you're getting, and how strong the data are in making your point. So this happened in case of Rachel's work, but Rachel and Jeff were looking ahead and had already these things in mind, and could respond to the queries from the reviewers. And then, of course, if you want to make your life easy at the end, we haven't talked about segmentation, that is its own beast, but you want to get as strong data as possible. So there are techniques to enhance the contrast, but then one again has to ask, are these techniques in any way changing the behavior of your material? So, but nevertheless, we have now, I think, enough really know-how, both on the sample preparation side as well on the data analysis side, to do this kind of work in a more routine fashion. And would love to hear back from you if you are interested. I would like to close the talk with an outlook. As I said, we have the possibility now on the size to do cryo-imaging in principle. And the basic motivation for that is that there are two basic motivators. One is that the staining of the traditional preparation technique blocks the fluorescent light information. And so therefore we have an incompatibility with fluorescence imaging, and so therefore we are depriving us of all these tools that are in principle available. And with vitrification, you have potential chance to get into that field. And the other aspect is sample preparation, dehydration, staining is changing your sample to some extent, and there are cases where it might actually render the information useless. So biologists like to vitrify samples to keep the sample in a state that is closer to the aqueous state. the Baumeister group in Garching was one of the leaders in this effort. And so the ideal experiment would be, for example, to have cells on a TEM sample, tag with fluorescence microscopy the objects, and then go in, prepare a TEM sample, and put it in our cryo microscope. So so this is potentially the future. So we're looking forward to get our feet wet. And in that context, I want to close and refer to two more masterclasses that are specifically dealing with cryo-imaging. The first one is Svetla. She's giving a talk about cryo-TM in the context of protein analysis. And then on the last talk, you will see a talk from Adam about cryo-SEM. So you can already get a sense of that topic from those two talks. With that, I would like to end. I hope I could give you a little bit an overview of where we are right now with that technique and where we are potentially going, and look forward to hearing back from you, and give back to David.